we'll see. Okay, so I don't know how closely you guys are reading the textbook. Maybe you guys have already read this Bordeaux wines example in the text. But it starts off in chapter 1. There's kind of this claim or an excerpt from an article that says this one guy, Robert Parker, tastes wines, and his score of a wine is like super influential on how well the wine sells. And then this other guy, Clive Coates, is also a wine taster, but his influence on wine sales is not important, even though he's super well respected as well. And so we're kind of just testing this out. We've gathered a bunch of data on different wines, and I don't know if you guys drink wine, but I am 0% the wine connoisseur. I just I'll taste it and go, this tastes good, and that's how it goes. But apparently, these guys know what they're talking about, and maybe their scores are very, very influential. And so we recorded a bunch of variables, and what we're interested in is how these things affect the y variable price. So we're looking at the points given by Parker, the points given by Coates, and then we have a bunch of dummy variables. Was the Parker score over 95? Was it a first growth? Is it a cult wine, or is it from Palmeral or a superstar? I guess these are, if you're into wine, these things matter. And we produced a bunch of for the dummy variables, for the categorical ones of whether it's a yes or a no. We can create box plots comparing these, and it seems like, okay, yeah, these things seem to have an influence on price. If we look at the points, there seems to be correlation between Parker points and Coates points, which is a good sign. Although this guy scored very low on Coates but high on Parker and things like that. There's a few outliers, but for the most part, if Parker rated it high, Coates also rated it high. And then we see, okay, there's maybe some kind of trend here, but there seems to be some kind of curvature there. So maybe we want to check these out. So where did it go? So when we look at the model, we're going to let me download our data. Okay, and so if we look at our data set, we've got price, and I don't know how these prices are measured. Actually, is it 2,000 per bottle? What is this? The price in pounds sterling of 12 bottles of wine. So 2,850 pounds. That's like $5,000 for I don't know, for 12 bottles. So what is that? That's a lot of money, right? We're looking at 237 pounds per bottle. So I guess about $400 a bottle. This one's even more. This one's a bargain at 150. But anyway, so anyway, here's our data, and I'm curious. I'm gonna look up one of these brands here, Le Pin wine, and okay. So we're gonna fit the model because of the curvature that we saw. The book suggests just starting off fitting the log price, log points, and for the two points variables, and then because the rest are all dummy variables, we're just you can't take the log on those. Okay, but we we can go back a few steps and see whether we should have transformed these or not. But we do it, and we fit the model. And it seems like everything's showing up significant with the exception of P95 and above. But we're fitting log price to the log of the Parker points and the log of Coates points. And Parker points is more influential than, or more significant, statistically significant, and the coefficient is higher. So there does seem to be some truth to what the article is saying. Okay. So we can also create plots of our standardized residuals. So if we just extract standardized residuals from M1, we have these. So we can, these are 85 standardized residuals, and we can plot these against each of our variables. So if we plot the log of Parker points versus the standardized residuals, this is what it looks like, and this looks pretty good. No crazy patterns there. Same thing with as far as points for Coates goes. Maybe a little bit more spread there. Okay, and as far as the dummy variables go, if we just did the traditional plot, it would not look so good, right? If I just did plot it would look like this, right? And I think some of you guys produce plots like this, and that's fine. But when you have a dummy variable like this, a box plot would be a preferable tool, just because you're only going to have a 0 and a 1, right? And so you can kind of get the spread, and it looks like, okay, there's a little bit more in terms of range for the ones, but as far as the kind of the amount of spread in the middle range, it's comparable. Okay, and we can look at these, and if we look at just the box without looking at the things, they look comparable, which is a good sign. And it might be, do we have to worry about the extreme points? Maybe, maybe not. Okay, we got some variation here, and as far as residuals go, it looks like more spread on the lower side for some of these things. Okay, and this one's kind of funny for that. Okay. Okay, and then and of course fitting our the fitted values versus the standardized residuals. This looks pretty good. Okay. And if we want to just look at the fitted values versus the y that we're doing, fitted values versus log of y, which is what we're going for, this looks like the model is very good. Okay, in terms of we've got a nice linear fit between what the model says and what we have. Okay, and we fit the model fit line, and that looks good. Okay, let's see. So again, looking at M1, the model, we have all of this. Okay, so there's a few tools that we can look at. One is variance inflation factor. Okay, so VIF. And maybe it is worth, that was from the other class. Okay, so the variance inflation factor, this is the idea behind kind of just a way to measure multicollinearity, meaning do our variables very strongly together, okay? And so if any of them are, over 5, or if you have a bunch of these where VIF is over 5, this is a point of concern, okay? And so we have Parker points over 5, and then we have P95 at 4, but Parker points is the only one over 5, so this means there's something here about Parker's points that very strongly with the other ones, but this is the only one that kind of hits high, and so we're not going to worry too much about it. But in another, I can't think of another example. But if we ran VIF for another variable or another data set, and it turns out that some of these predictors have high VIF, then we should worry a little bit and take a look at the added value plots, or added variable plots. Added variable plots to make sure the variables that we have in our model are contributing something. Okay, and I mean these tools all kind of go in conjunction together, in that usually if something is highly significant, okay, you've got a tiny p-value, then the added variable plot will show that it contributes something. And if you have something that has a high p-value, the added variable plot will show that it doesn't contribute a whole lot. And VIF also kind of goes in conjunction with that.
Question?
Yes.
So here we see Parker points has a high VIF, right?
Yes.
And that can indicate a linear relationship between that and some other variable?
Yes, it's right.
Wouldn't that mean that the other variable is also linearly related to this, and hence the high VIF as well?
Yeah. So yeah, everything is kind of related, and let me look up how this is calculated in of itself, but I'm not going to get this just from looking at this right here. I want to say the VIF here is high, meaning that the other ones, this is related to the other things, but in terms, I see, now I'm not so sure. I want to say this is if one variable, and I'm not saying that this is a direct combination of the other ones, but if it were a direct combination of the other ones, okay, we would expect this to be high, but because, let's say, these all combined together to form this one, which it's not, then any of them individually does not necessarily relate very strongly to this. But maybe these together combine to relate strongly to Parker points. But I want to say that's what's going on, although I am not 100% confident on that answer here. So yeah, the rule of thumb, if it's over 5, maybe it's worth considering, and if you got several of them hitting over 5, then you probably have a bunch of variables depending on themselves. Okay, on Friday we looked at low-S regression, the non-parametric form, and we plotted those versus the fitted values. There's a function built into package ALR3 called the marginal model plot, and what you do is the arguments that it accepts are the model that you're using and the variable that you're interested in, okay? And it creates a plot of kind of the variable versus the fitted values and the low-S regression line. And you want those things to be in agreement. So you want the MMP, the marginal model plot, to show the the fit line matching closely to the non-parametric lowest line, which is what we will see here. Okay, so the blue is what is fit via lowest regression, and the red is the line of predicted or fitted values from the model. Okay. Same if we used the coats. Okay, and so these are all good signs, and you can only really create these MMPs for the numeric variables. Okay, and we do this, and it seems like there's pretty strong agreement between our low S line and the fitted values. Yes.
Explain again what MMP does.
The marginal model plot. Yeah. So you're just plotting the fitted values. So let me. So I can create a plot between log price and log of Parker points. Okay, and I will get this thing, and then let me see. How do I forget how I do low S again. Low S. I want to do lines, low S, and log price, log Parker points, color equals red. Okay, so this is so that's okay. So the low apparently I think they're using low S with the without the W, which gives us a more kind of a little bit more of a jagged line. Let me just okay, so I think they're using the other one with the without the W, which gives us a little bit more of a slightly more jagged fit, the blue line. Okay, and then what we have, what we're going to do is compare the fitted values. So what do I want? I want M1 $ fitted values as explained by log Parker points, and I want to add this lines color equal, we'll do black. Oh no. Oh gosh. Of course. I think I have to sort this. Is this right? Oh, this is gonna get me in trouble here. I know it. Yeah, of course. Let me. No. Why am I getting this? I need something smooth. Oh, because I'm using fitted values. Oh, I have to do predict. That's what I have to do. Okay, hang on. Sorry. Okay, just because I'm being put on the spot here. So let me do. So I have to create a prediction thing based on our model and fitted values. So. Okay, so I have to do predict based on M1. I want, so my sequence will be from minimum of Parker points to max Parker points. sequence length. No. Our output length. What is the what are the arguments for sequence? Length out equals 100. This will be our x predict, and for predict, I put in an object and x, and what do I do? Log Parker points is equal to log of xx. Okay, I think this will do it. No? Sad face. Okay.
It's okay. I just want to know.
All right. No, it's basically we're just we have the dotted red line that fits the fitted values according to the model based on this variable Parker points, and we are comparing it to a non-parametric curve based on the data. So the non-parametric from the low S was just, here's our local regression based on these data points that we have, and we're just trying to compare those two things. And ideally, when you have the fit values, they line up closely to what the non-parametric regression does. Okay. Anyway, sorry, I spent too long trying to figure that out. Okay. Anyway, we look at the summary here. We can look at the added value plots. Okay, so we just throw AV plots of all of these things, and we look at all of these, and it seems indeed everything seems to be related. Okay, with the exception of P95 and above, this one's the only one that's kind of flat. All right, and so so we can throw this away. Okay, so we throw away this one, and we fit our revised model. Although now I just got 50 warnings here. What did I do? Okay. I'll have to see why I'm getting all these warnings. Okay, and then and we do this, and this is our model. Good thing. Okay. I have to finish our my slides also for on model selection. Okay, so I think today I'm just going to kind of create a big picture overview of how these model selection things go. So as you know, with this Bordeaux wine example, we just kind of said, oh, this one's not significant, let's throw it away. Okay, and we did that, and that's fine. Okay, but sometimes you're going to have kind of competing models, and you'll have a few things, and you'll say, you know, well, should I keep this guy here, log Coates points? Okay, you know, it is significant. What happens if I remove him? Okay, and you have to kind of balance the idea between do I include a bunch of things to try to make predictions, or do I try to parse down my model to be as simple as possible? And I guess that depends on you, your decision making, what you prefer. You know, when you throw in too many predictors, you run the risk of overfitting. So overfitting is the idea of, say here, just you know, do we want to use many predictors or fewer predictors? Okay. Too many predictors That's, you know, could lead to overfitting. Or overfitting is really the idea of having too many predictors. That you are now, and part of your model includes just some of this. There's not a true pattern there, but because of just some weird oddities in your data, you are saying that this pattern exists. Okay, so maybe you wore a certain T-shirt, and when you took a test, and you got a high score on your test, and then maybe the next week, by coincidence, you happen to be wearing the same T-shirt, and you also happen to score high on the test that week. Okay, and so now in your brain, because we do this as humans, you think, this is my lucky T-shirt. I'm going to wear this to every test. Okay, now what's happening there is your brain is, quote, overfitting, in that it sees something kind of unusual that does exist in the data, where, when the T-shirt was worn, the test scores were high. That does exist in the data that was observed, but it's not necessarily a reflection of what's happening in the population if we were to continue this. Okay, and so if you pick too many predictors, so if your predictor is, did I wear this T-shirt or not, that might turn out to be significant in the small, in your samples that you have, but it may not necessarily actually exist in the population. Okay, so that would be overfitting. So, from our random sample, we pick up on a pattern that seems to exist in our data, but does not actually exist, in the population. Okay, so we don't want to do that, but at the same time, we want to make our model as good as possible in terms of making predictions. I have this set as okay. So we have a few tools. One is adjusted R-squared, which gets spit out every time you run the model. Okay, so you run summary M2, and it spits out your adjusted R-squared right here, 0.9205. When we look over here, 0.9199, and we say, oh, this is a little bit higher. This model is better, or something. This is all of these tools in of themselves should not just be the end-all be-all for decision making. Okay, so adjusted R-squared does take into account the number of predictors used. Okay, so because as you increase the number of predictors, the regular old R-squared value will almost always go up. Okay, the regular old R-squared value almost always goes up when you include more predictors. So in Model 2, we are one predictor fewer. We have one predictor less than in Model 1 when we're looking at these Bordeaux wines. Okay, and so so when we include P95 as this is the Parker 95 score, not I don't know that workout video, but when we include this, our multiple R-squared does happen to go up just ever so slightly. Okay, this is 1 minus the residual squared type of thing. Okay, percentage that's explained by the model. And the adjusted R-squared takes into account how many predictors are being used, and so that actually goes down because we're including an additional predictor. Okay, so this is one way to measure it. Okay, we also have AIC and BIC. Okay, AIC stands for Akaike Information Criteria. Okay, criterion. Akaike. Yeah, it was by this guy, Akaike. Okay. Um, and it takes into what it does is it calculates a value for the likelihood of the data under the model. Okay, and so the likelihood is just another word for probability. It's basically the probability of the data, but when we talk about the likelihood, we're almost always talking about data. So we just say, you know, if this model is correct, what is the probability of getting this particular value? And we calculate the probability for all the data points that we have, and then we multiply them all. Okay, so these likelihoods are incredibly small numbers, and we take the log of the likelihood, and we get like, you know, negative 1,000 points or something. But right, because it's like, you know, you flip a coin 10 times and you get heads, heads, tails, tails, heads, tails, heads, tails, heads, and it says, you know, what's the probability of getting this exact sequence? It's going to be small, but when you do it that way, you can make comparisons between models. Okay, and we with AIC, what we're doing is we also take into account the number of parameters. Okay, and so we're taking the negative of the log likelihood. So this becomes if it's more likely, the you get a negative of a thing that's less negative. So so anyway, with AIC and BIC, which is similar in concept, smaller numbers are better. Okay, smaller numbers for AIC, the Akaike, and I'll write all of this in the notes. I'll finalize my notes here. A smaller number is better. BIC, a smaller number is also better. There's also a corrected AIC, which our book talks about, and gets this little section in Wikipedia, AICC, and basically it kind of gives a larger penalty with the number of parameters. So K is the number of parameters being estimated by the model, and so the corrected one, I guess, takes into account the sample size with the number of parameters, saying as the sample size increases, and you also increase the number of parameters, you know, the penalty should be different. Okay, BIC, which is related, I probably, oh no, it doesn't show up here. Let me see. Okay, is very similar. Okay, so if you look at the formula for AIC, which is this thing, 2k minus 2 ln of L, the likelihood. So we have minus 2 ln of L here, okay? And but rather than adding 2k, they change the order here. They're doing k times ln of n, okay? So k is the number of parameters here, and so here the BIC gets bigger. Every parameter you add, the BIC gets bigger by a factor of ln of n, okay? Which is almost always bigger than 2, okay? ln of n is bigger than 2 if n is, oh, I don't know. I think I want to say bigger than 8. So if you have more than 8 data points, okay, in your data set, which is almost always, you're going to get a bigger penalty for including an additional parameter in estimation here. Okay, so the BIC puts a stronger penalty for including another parameter. All right, so depending on which criteria you decide, okay, AIC or BIC, can help you choose which model is a good model to use. In general, most of these things will be in agreement. Okay, so as the model gets to be better, your adjusted R-squared is expected to go higher, and your AIC is expected to go lower, and your BIC is expected to go lower also. And if you have these models, you can get AIC from R. You just type in AIC, and you say AIC M1 versus M2, okay, and all removing the extra parameter for M1 and getting M2, we get a slightly lower AIC here, okay? And so this would kind of indicate this is a better model. But there's no magical rules here, okay? So you might try a model and the AIC could be like 1,000 points or something. It could be huge. And you try another one and it might decrease that by a little bit or a lot. We don't have like statistical tests that say with this AIC it's good and with this AIC it's bad, or with BIC same type of thing. I think there's also extract AIC, same concept here, and we're getting different numbers. How is this possible? They're all just kind of they're controlled by I want to say there's just a constant being thrown in here that kind of can change things. But in terms of the difference in terms of the values, they should be at least similar, I want to say. AIC M1, let's see, minus AIC M2, we're getting a difference of 1.397, and let me see. Yeah, so the difference between 34.74 and 33.35 is the same as the difference between negative 171.58 and negative 172.97. They're just depending on some they're like similar in terms of the differences, but they might just be moved up and down the number line. Okay. This is I think the number of parameters being estimated. So I want to say, let's see, 1, 2, 3, 4, 5, 6, 7 are being estimated for Model 2, and then over here 8 are being estimated. If you want to get the BIC, you have to, I want to say, you have to change this one, the K. So the K is equal to 2. So we have to say, I think in Bordeaux wines there was 82. So we would do n equal to 82, and then we would do log n, and we would use this as our factor for to get our BIC. So extract AIC is this, and we would say K is equal to log n, not log n, okay, and for Model 2, okay, and then so we can see that with the BIC using log n versus rather than 2, the difference between this model and this model in terms of the information criterion, this one is even lower. So the BIC would favor this one even more. Okay, so we'll try some real examples with this on Wednesday and whatnot. But these are just kind of tools that exist in terms of just helping us decide whether one model is good or not. There is the and we'll see if we get to it. The likelihood ratio test, which is a hypothesis test on whether or not you should include a certain variable. But as far as just kind of evaluating model fit, these are just kind of tools that spit out a number, and with the hope that you're gonna use them as a guide to help pick your number, pick the model. But there's no test that says this is good or this is bad. Okay. Okay, we'll end there, and we'll see you guys Wednesday. Oh, so I'm also trying to write a homework assignment for this class, and so I'll get that posted, and you guys can work on that also. All right.